Hello, astronomy enthusiasts from all over the world. I'm Luis Miguel Azorin, and I welcome you once again to a new Astro Academy video. As you know, this is your YouTube channel, your podcast, and your online academy about what we are passionate about: astronomy, astrophotography, and everything related to the universe and space. If you're passionate about astrophotography, you've probably heard of CCD and CMOS cameras, but do you really know what the differences are between them and why CMOS sensors dominate the market today? In this video, we're going to explain the characteristics of both types of sensors, how they perform in terms of signal and noise, and finally, why CMOS sensors have taken over, even though at first they seem destined to disappear. We'll also look at what CCDs historically contributed and why current CMOS technology has managed to surpass them. Let's start with the basics. CCD, or charge-coupled device, was the dominant technology in astrophotography for decades. Each pixel transfers its charge to the next one, until it reaches the readout circuit. This produces very uniform images with low noise, ideal for long exposures and for capturing extremely faint details in deep sky objects. For its part, CMOS, or complementary metal oxide semiconductor, reads each pixel independently. This obviously allows for greater speed, flexibility, and internal processing. In addition, they consume less power. Initially, the first CMOS sensors seemed inferior to CCDs because their read noise was higher and their uniformity was much lower. The fundamental difference is how the light is processed. CCD concentrates all the information in a single readout circuit, while CMOS distributes it per pixel. This has implications for noise, speed, dynamic range, and camera control. Let's summarize their advantages and limitations. In terms of read noise, CCD wins, or used to win. It had very low red noise. In CMOS sensors, it's low to moderate, although in recent models we can already say it matches or even surpasses CCD. As for capture speed, it's low in CCD, while in CMOS it's high and allows for rapid sequence image captures. This is especially interesting in the practice of planetary astrophotography, where we usually capture video sequences, not individual images. If we pay attention to energy consumption, we see that CCDs have high energy consumption, while in CMOS it's radically different. Energy consumption is low. And if we pay attention to one of the most important aspects between these two types of sensors, the price, we see that CCD sensors are more expensive than CMOS sensors, which are usually positioned in a much more affordable price range for enthusiasts. And finally, if we think about the flexibility each type of sensor offers us when working in different situations, we see that CCDs give us much more limited flexibility than CMOS, which allows for very high flexibility with regional control, binning application, internal processing. Therefore, we can summarize that the CCD sensor is ideal for long, deep exposures and mainly for scientific astrophotography, whereas CMOS is a more versatile sensor that is suitable for practically everything, though it doesn't particularly stand out in the scientific field the way CCD does. CMOS would be ideal for astrophotography of all kinds of general objects, whether planetary or deep sky, for use in remote observatories due to the flexibility and speed it offers us, and so on. In summary, CCDs used to be the benchmark for image quality and uniformity, especially for scientific studies and professional astrophotography. Modern CMOS sensors have matched and even surpassed many of the advantages of CCDs, while also offering greater flexibility, higher speed, and crucially, lower cost. Another interesting point, CCDs require more complex circuitry and more powerful cooling, whereas modern CMOS sensors already integrate many internal functions that previously could only be achieved with additional hardware. Nowadays, CMOS sensors are becoming more and more complete and efficient, while also getting cheaper. Two key concepts when comparing sensors: signal-to-noise ratio and dynamic range. The signal is the actual information we capture from the photographed object. Noise is the interference that makes it harder to see the details. With these concepts in mind, historically, CCDs have had very low red noise, ideal for capturing extremely faint objects in long exposures. Modern CMOS sensors, on the other hand, are offering increasingly lower read noise, reaching levels comparable to or even better than CCDs under certain conditions. And they also offer a greater dynamic range, which allows you to capture both bright stars and faint nebulae in the same image. This has historically been a problem with CCD sensors, which tend to blow out the brightest stars due to that lack of dynamic range. Additionally, CMOS sensors allow for very precise adjustment of gain and offset, something that was more rigid in CCDs. This gives us greater control with CMOS sensors for different types of exposures and objects. So if you're still wondering whether it would be better for you to get a CCD sensor or a CMOS sensor nowadays, what should you take into account? CCD is still useful for very specific tasks, such as precise photometry, scientific astrophotography, or very long deep sky exposures with great uniformity in the captures. CMOS, on the other hand, is extremely versatile, ideal for remote observatories tracking multiple types of objects, fast captures, which is key in planetary astrophotography, where these sensors have become the absolute kings, and experimentation with filters thanks to the speed and versatility of this type of sensor. Nowadays, few enthusiasts buy a CCD unless they are looking for very specific features, because the available models are old and expensive. Current CMOS sensors cover the vast majority of needs that a user might have in this hobby efficiently and at a much more affordable cost than buying a CCD. So, why have CMOS sensors definitively overtaken CCDs? Well, I think with everything I've told you, it's already pretty clear. When the first CMOS sensors hit the market, many thought it was a technology destined to disappear. They didn't offer the uniformity or low noise of CCDs and seemed destined only for budget or general consumer cameras aimed at people with a tighter budget. However, CMOS technology has evolved tremendously. Significant noise reduction, better dynamic range, even surpassing that of CCDs. Much higher readout speed, in fact, much higher. And this is especially noticeable with the evolution of larger sensors, APS-C and even full frame. Lower energy consumption, greater flexibility for automation, and above all, sensors that are ideal for remote observatories. This has led manufacturers and enthusiasts to choose CMOS almost exclusively, relegating CCDs to a very specific niche. Today, CCDs survive only in scientific or highly specialized applications, and acquiring them is complicated and expensive. CMOS sensors have prevailed not only because of their performance, but also due to their versatility and ease of use, making them the preferred option for the vast majority of astrophotographers. In summary, CCD and CMOS represent two different approaches to capturing astronomical light. CCDs offer uniformity and low noise, but modern CMOS sensors combine these advantages with speed, flexibility, lower power consumption, and more affordable cost. That's why CMOS sensors have become dominant in modern astrophotography, and understanding their characteristics allows us to choose the right camera according to our goals and style. In upcoming videos, we'll dive deeper into how to configure your camera, adjust gain and offset, and optimize results from your own telescope or your remote observatory. If you're interested in astrophotography and want to learn all these concepts with a solid foundation, subscribe to the channel and turn on the notification bell. See you in the next Astro Academy video.